Greatest common factor. To better understand the greatest common factor, we must first review what is meant by a factor. Consider the number 12. What two positive integers can we multiply together to obtain 12? 1 times 12 results in 12. 2 times 6 results in 12, as does 3 times 4. The numbers involved in each of these products are called factors. So 1, 2, 3, 4, 6, and 12 are considered factors of 12. When two or more numbers share a factor, it is called a common factor. Consider the numbers 12 and 18. We saw above that the factors of 12 are 1, 2, 3, 4, 6, and 12. The factors of 18 are 1, 2, 3, 6, 9, and 18. Notice that the two numbers have several common factors. 1, 2, 3, and 6 are all common factors. The greatest of these shared factors is the greatest common factor. So the greatest common factor of 12 and 18 equals 6. 6 is the largest common factor that divides both numbers. Now consider example 1, in which we're asked to find the greatest common factor of two expressions involving variables. Consider the first expression, x squared y to the fifth z, all being multiplied together. The factors of this expression consist of the product of two x's, since we have x squared, the product of 5 y's, since we have a y to the fifth, and then a factor of z. The factors of x squared y to the fourth consist of a product of two x's, since we have x squared, and a product of 4 y's, since we have y to the fourth. Comparing the two sets of factors, we see that both expressions have a common factor of x squared, and both expressions have a common factor of y to the fourth. So the greatest common factor of these two expressions is equal to x squared y to the fourth. Being able to determine the greatest common factor is extremely important when we're asked to factor completely. When told to factor completely, we always begin by factoring out the greatest common factor. So consider example 2a, in which we're adding two terms. We're being asked to factor completely, which means that we need to write this as a product. So we look at each term and we ask ourselves, what is the greatest numerical factor that divides both coefficients? And the answer is 8. 8 is the largest factor that divides both the coefficient of 8 and the coefficient of 16. Next, we look at the variable parts. In the first term, we have a factor of x to the sixth. In the second term, we have a factor of y to the fourth. Neither term has any common variable factor. Therefore, 8 is the only factor that we can divide out of each term. When we factor 8 out of each term, we're left with 1x to the sixth plus 2y to the fourth. Whenever we factor, we can always check our answers by multiplying the expression that we get from factoring to see if we get back to the original expression. So notice if I were to distribute the 8 through the set of parentheses, I would get exactly what I started with. Now consider example 2b. We're asked to factor 10y to the 9th minus 2. Looking at the numerical factors in each term, we ask ourselves what is the largest number that divides both 2 and 10, and the answer is 2. Now looking at the variable factors, in the first term we have a factor of y to the 9th. In the second term, we have no y factor at all. Therefore, 2 is the greatest common factor, since there is no common factor involving y. Dividing 2 out of each term results in 5y to the 9th minus 1. Notice when we divided the second term by the 2, 2 divided by 2 gives us 1, so we must have a factor of 1 left behind. Checking our answer by multiplying the 2 through the set of parentheses, notice that we do end up with 10y to the 9th minus 2, the exact expression we started with. Now consider 2c. Looking at our two terms and focusing on the numerical factors, the largest number that divides both 15 and 9 is the number 3. Looking at the variable factors in each term, we see that the first term has an x to the first, and the second term has x cubed. So the two terms have a common factor of x. So the greatest common factor for these two terms is the term 3x. After dividing each term by 3x, we're left with 5 plus 3x squared. Again, we can check that we have factored properly by multiplying the expression that we've written in factored form to see that we get the same expression that we started with. We continue factoring completely in example 3. Consider part A, in which we're asked to factor 12x to the 7th minus 20x to the 8th. Looking at our numerical factors, the largest number that divides both 12 and 20 is the number 4. Looking at our variable factors, the largest factor involving x is x to the 7th. So our greatest common factor is 4x to the 7th. And when we divide each term in our original expression by 4x to the 7th, we're left with 3 minus 5x. In example 3b, we have 3 terms in our original expression. Looking at the numerical coefficients, we notice that the only common factor amongst those 3 coefficients is the number 1. So moving then to our variable factors, we see that the greatest factor involving x is x squared. So our greatest common factor in this example is simply x squared. And dividing each term by x squared leaves us with 14 plus 17x plus 13x cubed. Now consider example 3c. Looking at the numerical coefficients of each term, the largest numerical value that divides both 16 and 24 is the number 8. Looking at our x factors, the largest factor involving x is x cubed. Finally, looking at our y factors, the largest factor involving y is y to the 4th. So our greatest common factor is the product 8x cubed y to the 4th. And dividing each term by that common factor leaves us with 2x to the 6th minus 3y squared. And at this point, there's nothing left for us to do. Factoring trinomials, Part 1. Before we begin our discussion of factoring trinomials of the form 1x squared plus bx plus c, we must first practice multiplying binomials together. In example 1, we're asked to multiply 4 pairs of binomials. Notice the similarities between these 4 pairs. In each pair of binomials, the first term of each binomial is an x. Furthermore, the second term of the first binomial consists of a 2, and the second term of the second binomial consists of a 9. The only difference between the 4 pairs is the operation that connects the 2 terms in each binomial. So let's begin with example 1a. We're asked to multiply x plus 2 times x plus 9. Applying the distributive property, we will begin by multiplying the first 2 terms in our binomial pair. So we have x times x, which gives us x squared. We then move to multiplying the outer terms. The first term of the first binomial, the second term of the second binomial. X times 9 gives us a positive 9x. Then we multiply the inner terms. That is, the second term of the first binomial and the first term of the second. Positive 2 times x is a plus 2x. And finally, we multiply the last terms. 2 times 9 gives us a positive 18. To complete our multiplication process, we now combine like terms. Notice that we end up with x squared plus 11x plus 18. Now let's use the same multiplication process to multiply the remaining 3 pairs of binomials. In example 1b, we start with first x times x, outer plus 9x, inner. Here we have a subtraction of 2x since a negative 2 times a positive x is a negative. And then last, negative 2 times positive 9 is negative 18. When we combine like terms, we have x squared plus 7x minus 18. Now we're beginning to see some differences between the results that we see in A and B. But before we try to generalize, let's continue the multiplication process. So consider example 1c. First, outer, inner, last. Combining like terms, we end up with x squared minus 7x minus 18. One more example. X minus 2 times x minus 9. First, outer, inner, last. Negative 2 times negative 9 is a positive 18. Combining like terms, we have x squared minus 11x plus 18. Now let's compare our answers. Recall that we multiplied two binomials that were identical with the exception of the operations occurring between the two terms in each binomial. If we look at A and D, the third term in each of those trinomials is positive. And recall, to get that third term, we multiplied the last two numbers in each binomial. Notice, to get a positive 18, we multiplied a positive times a positive, or a negative times a negative. Furthermore, notice that the operation occurring between the first and second term of our trinomials matches the operation that appeared in the binomials. And finally, notice that the 11 coefficient that appears in both of the middle terms of our trinomials is equal to the sum of the two numbers that appeared in the binomials. Now consider B and C. The third term in each of those trinomials is negative. And to obtain that negative 18, we multiplied a negative times a positive, or a positive times a negative. Also notice that the 7 that appears in both of the middle terms in each of these trinomials is equal to the difference of 9 and 2. The sign in front of that 7 depends on where the addition and subtraction symbols appear in the binomials. Although we don't need to memorize these patterns, noticing these patterns will help us to factor trinomials of the form 1x squared plus bx plus c. Now let's try to factor the trinomial x squared plus 9x plus 20. Notice that this trinomial is written in descending order and is of the form 1x squared plus bx plus c. If this trinomial factors, it will be written as a product of two binomials. Based on our observations in example 1, we know that the factors of x squared will go in the front of each binomial. Since x times x gives us x squared, we know that x will be the first term in each of our binomials. Based on our observations in example 1, we also know that the positive 20 gives us the numbers in the back of each binomial. Specifically, the factors of positive 20 will give us what we need. Since this is a positive 20, that tells us that the numbers that we place into our binomials must have the same sign, because in order to get a positive when multiplying two numbers together, they must both be positive or both negative. To determine what that sign is, we consider the sign of the middle term. Since the middle term is positive, that tells us that both factors of 20 that we place into our binomial will be positive. Now consider what the factor pairs for 20 are. 1 times 20 gives us 20, as does 2 times 10, and 4 times 5. When trying to determine which factor pair to use in our binomials, we must remember that our inner product plus our outer product must equal the 9x in this case, the middle term in our trinomial. So if we look at the factor pair of 4 times 5, notice that 4 plus 5 does give us the 9 that we need. So if we attempt to factor by placing plus 4 and plus 5 into our binomials, we will need to check to see if we've obtained the correct factorization. That is, we multiply the inner, which is 4x, and we add that to the product of the outer, which is 5 times x. And when we add those together, we get 9x, which is a good thing because we want it to match the middle term of our trinomial. So based on our work, we can conclude that x squared plus 9x plus 20 can be factored as x plus 4 times x plus 5. Now consider example 3, in which we're given the trinomial x squared plus 3x minus 18. Again, this trinomial is of the form 1x squared plus bx plus c. So if it factors, it will be written as a product of two binomials. The factors of x squared, as in the previous example, go in the front of each binomial. So each binomial begins with an x. The factors of negative 18 go in the back of each binomial. Since this number is negative, that tells us that the factors that we place into our binomials will have opposite signs. So now let's consider the factors of 18. 1 times 18 gives us 18, as does 2 times 9 and 3 times 6. When trying to determine which factor pair to use, we must remember that the inner product plus the outer product is supposed to equal the 3x that appears in the middle. Also keep in mind that these factor pairs will have opposite signs. So when you're looking at those factor pairs, you must keep both of those facts in mind. So let's take a look at the last factor pair, 3 times 6. Notice that we can get a positive 3 by adding a negative 3 plus 6. Opposite signs, which will lead us to the negative 18 when we multiply. But when we add, notice we get the positive 3 that we need. So let's try placing minus 3 and plus 6 into our binomials. Notice that negative 3 times positive 6 does give us the negative 18 that we need. When we multiply the inner product, negative 3 times x, we have negative 3x. The outer product is x times 6, or plus 6x. When we add those two terms together, notice we do get 3x, which is what we need it to be. This means that we can conclude that x squared plus 3x minus 18 can be factored as x minus 3 times x plus 6. Example 4 gives us the trinomial x squared minus 5x minus 6. Setting up the product of two binomials and placing the factors of x squared in the front of each, we now focus on determining what factors of -6 to put in the back. Since this third term is negative, that tells us that the factors of -6 that will go into our binomials will be opposite in sign. So let's consider the factor pairs for 6. There's only two such pairs, 1 times 6 and 2 times 3. Keeping in mind that these two numbers must be opposite in sign, and also keeping in mind that the inner product plus the outer product should equal the -5x that we need it to be, since that is the middle term. We see that the first factor pair is the one that we're going to need, since we can get a -5 by taking 1 plus a -6. Notice the opposite signs. 1 plus -6 does give us a -5. So let's try placing +1 and -6 into our binomials. Positive times negative gives us the -6 that we need, but then multiplying the inner product, we have 1x plus the outer product, which is -6x. And when we add those together, we do get the -5x that we need. Therefore, the factored form for x squared minus 5x minus 6 is equal to x plus 1 times x minus 6. Now I will make a note here that you should be careful on this one, because if you notice, you can get a -5 using the factors of 2 and 3 by taking -2 plus -3, which gives us -5. However, notice that this is not an option, since those two numbers have the same sign. They both involve negatives. And remember, we determined at the beginning that the numbers we choose must have opposite signs in this example. So the bottom line is that you want to make sure that you check by multiplication to ensure that you have found the actual factorization. In example 5, we have the trinomial x squared minus 9x plus 14. Setting up our product of binomials, placing our factors of x squared in the front, we now need to concern ourselves with determining the factors of positive 14 to put in the back of each binomial. Since this third term in the trinomial is positive, that tells us that the factors we choose must have the same sign. To determine whether they're both positive or both negative, we look at the middle term. Since that middle term is negative, that tells us that both numbers that we place into our binomial must be negative. So now let's determine the factors of 14. 1 times 14 gives us 14, as does 2 times 7. And that's it. So remember, the two factors that we choose must have the same sign, in fact, both negative. And ultimately, we want our inner product plus our outer product to equal negative 9x, that middle term in our trinomial. So we will choose the factor pair of 2 times 7, since negative 2 plus negative 7 gives us negative 9. Notice that both the 2 and the 7 have a negative, which is what we had decided it should be from the start. And negative 2 times negative 7 gives us the positive 14 that we need. So let's now check by placing minus 2 and minus 7 into our binomials and multiplying our inner product, which is a negative 2x, plus our outer product, which is negative 7x, adding them together to obtain the negative 9x that we need it to be. So the factored form for x squared minus 9x plus 14 equals x minus 2 times x minus 7. Example 6 has us factoring x squared minus 10x plus 25. Setting up our product of two binomials with an x in front of each, we now look at the third term in the trinomial at positive 25 and think about what factors of positive 25 need to be placed in the back of each binomial. Since that is a positive 25, we know that the numbers we choose must have the same sign. Furthermore, since the sign of the middle term is negative, we know that both numbers we choose must be negative. So, considering the factor pairs of 25, 1 times 25 and 5 times 5, and keeping in mind that the inner product plus the outer product is supposed to give us negative 10x, that middle term in our trinomial, we can determine that the 5 and the 5 make up the factor pair that we need. In fact, negative 5 plus negative 5 does give us the negative 10 that we're seeking. And negative 5 times negative 5 gives us the positive 25 that we need. So let's try putting minus 5 minus 5 into our binomials. Our inner product will be negative 5x. Our outer product is also negative 5x. And when we add those together, we get the negative 10x that we need. So the factorization of x squared minus 10x plus 25 is equal to x minus 5 times x minus 5, which could be written more compactly as x minus 5 squared. Factoring trinomials, Part 2. Factoring trinomials of the form ax squared plus bx plus c, where a doesn't equal 1, is a bit more challenging. Consider the trinomial in example 1. 8x squared plus 19x plus 6. First, note that there is no common factor among the three terms in the original trinomial. There is no numerical value that we could divide out of each of those terms. Furthermore, the third term doesn't have an x. So if this trinomial factors, we will still get the product of two binomials. And the factors of the first term will still go in the front. However, we have more options than we had when the x squared term had a 1 in front of it. So keep in mind that the factors of 8x squared must go in the front. So we know that there's going to be an x in both. But we have options for the factors of 8. You can get 8 by multiplying 1 times 8 as well as 2 times 4. So we have choices. Furthermore, the factors of the positive 6 at the end of the trinomial will go in the back. 6 has two factor pairs as well, 1 times 6 and 2 times 3. So there are many options here, and that's what makes factoring trinomials of this form a bit more challenging. However, we have to start somewhere, so let's begin by using the first factor pair for 8. At this point, it doesn't matter where we place those two factors in our binomials. That is, we can place the 1 in front of the x in the first binomial and 8 in front of the x of the second binomial, or we can reverse those placements. At this point, it doesn't matter. Now let's consider the factors of 6. Again, we have to start somewhere, so let's go with the first factor pair, 1 and 6. Where we place these two factors in our binomials does matter, since 1 and 8 have already been placed into our binomial. So let's suppose that we place plus 1 in the first binomial and plus 6 in the second. I know straight away that there is a problem, because now I notice in the second binomial the two terms have a common factor of 2. I know this is a problem because recall, at the beginning we noted that the original trinomial had no common factor. If the original trinomial has no common factor among the terms, then there will be no common factor within a binomial of the factored form. So that tells us that the 6 cannot be placed with the 8. Perhaps it can be placed in the other binomial instead. So let's erase our 6 and our 1 and switch their locations. That is, let's put the 6 in the first binomial and the 1 in the second. Now neither binomial has a common factor, which is a good thing. So we're confident that 1x times 8x gives us the 8x squared in the front of our trinomial, and we're confident that plus 6 times plus 1 gives us the positive 6 at the end. The question now is whether the sum of the inner product and the outer product give us the middle term. So let's check it out. The inner product, 6 times 8x, is 48x. Add that to the outer product, which is 1x times 1, or just 1x. If we add those together, we get 49x, which does not equal the 19x that we need it to be. So that tells us that something's wrong. The question is it the factors of 8 that we used? Is it the 1 and the 8? Or is it the 1 and the 6? At this point, we don't know. It's best not to change both of those at one time, however. So let's leave the factors of 8 that we have chosen, the 1 and the 8, and let's move to the factors of 6 that we have not yet tried, the 2 and the 3. So again, we erase, and we're going to replace the 1 and the 6 with our factors of 2 and 3. So suppose we put the 3 in the first binomial and the 2 in the second. We can know straight away that this is wrong because notice that the second binomial has a common factor of 2, which cannot be possible since our original trinomial does not have a common factor. So let's try putting the 2 in the first binomial and the 3 in the second. Feeling confident that we have the 8x squared term and the 6 based on how we've determined what terms to put in our binomials, we really only need to check the sum of our inner product and our outer product. Our inner product is 2 times 8x, or 16x, plus our outer product is x times 3, or 3x. And notice when we add those together, we do get 19x, which is what we wanted. So we can conclude that the factored form for 8x squared plus 19x plus 6 is equal to x plus 2 times 8x plus 3. Example 2 asks us to factor the trinomial 6x squared minus x minus 12. Notice that the 3 terms in this trinomial have no common factor. This means that when we are in the process of determining our binomials in our product, that there should be no common factor within one of those binomials. We do know now that the factors of 6x squared must go in the front. So that tells us that each binomial will start with an x term. The factors of 6 that could potentially be the coefficients of those x terms consist of the factor pairs 1 and 6, or 2 and 3. The factor pairs to go at the back of each of those binomials comes from the factors of negative 12. Since 12 is negative, that tells us that the factors we place into our binomials will have opposite signs. The factors of 12 that we will need to consider are 1 and 12, 2 and 6, and 3 and 4. Again, we have many options, but we have to start somewhere. So let's suppose we begin with the factor pair for 6 involving 2 and 3. Where we place these coefficients does not matter at this point. So let's go ahead and put 2 in front of the x in the first binomial and 3 in front of the x of the second binomial. Going to our factors of 12, again, we have to start somewhere. So let's suppose we start with the factors of 3 and 4. Where we place these numbers in our binomials does matter. Suppose we chose to put the 4 in the first binomial and the 3 in the second. Before we even get to the signs, notice that we have some issues because the first binomial now has a common factor of 2, and the second binomial has a common factor of 3, which shouldn't happen since the original trinomial had no common factor. So that tells us that we've placed the 4 and the 3 in an inappropriate place. So let's try placing the 4 in the second binomial and the 3 in the first. Now recall, the signs of these two numbers should be opposite. So that means one of them should be a positive and one should be a negative. So, not knowing which should be which, let's just go ahead and try placing a positive with the 3 and the minus, the subtraction, the negative with the 4. Okay, so we now know that 2x times 3x does give us the 6x squared. And we know positive 3 times negative 4 does give us the negative 12. But do we have the middle term when we add the inner product of 9x to the outer product negative 8x? Notice when we add the inner and outer products, we get 1x. But we need negative 1x. So that tells us that our signs are misplaced. So let's erase again and place the minus with the 3 and the plus with the 4. How does that change our inner and outer products? Well, our inner product is now a negative 9x, and our outer product is now a positive 8x, and if we add these two terms, we get the negative x that we needed. Therefore, we can conclude that the factored form for 6x squared minus x minus 12 is equal to 2x minus 3 times 3x plus 4. In example 3, we're given the trinomial 49x squared plus 28x plus 4. Notice that there is no common factor among the three terms in that trinomial. Moving straight into factoring, we look for the factors of 49x squared to place in the front of each binomial. Considering the factors of 49, there are two factor pairs for 49, 1 and 49 and 7 and 7. So we have to start somewhere. Let's go ahead and start with the two factors 7 and 7. So let's put 7x in front of both binomials. Now we look to the last term to determine the possible numbers to put at the back of each binomial. Since that number is positive, that tells us that the numbers we place into our binomial will have the same sign. Furthermore, since that middle term is positive, the sign that we will use for our factors of 4 will be both positive. Now the number 4 also has 2 factor pairs, 1 and 4, along with 2 and 2. Keeping in mind that we need to have our inner product plus our outer product equaling 28x. Anticipating this, we can see that it's probably in our best interest to choose the factor pair involving 2 and 2. So let's put our plus 2 and our plus 2 in both binomials. We're confident that we have our 49x squared by multiplying 7x times 7x. We're confident that we have our positive 4 by multiplying a positive 2 times a positive 2. We only need to check our inner product of 14x plus our outer product of 14x. And notice we do get a sum of 28x, which is what we needed. So 49x squared plus 28x plus 4 can be written in factored form as 7x plus 2 times 7x plus 2, or more compactly as 7x plus 2 squared. In example 4, we are factoring the trinomial 30x squared minus 29x plus 4. Notice that the 3 terms in this trinomial do not have a common factor. So we can go straight into setting up the product of 2 binomials. The factors of 30x squared will go in the front of each binomial. Considering the number 30, it has several factor pairs. 1 times 30, 2 times 15, 3 times 10, and 5 times 6. Many options. But we have to start somewhere, so let's begin with the last factor pair involving 5 and 6. At this point, it doesn't matter where we place those 2 factors. So let's go ahead and put 5x in the first binomial and 6x in the second. Now the factors of 4 will be placed in the back of each binomial. Since this third term in our trinomial is positive, that tells us that the 2 factors we place into our binomials will have the same sign. In fact, since that middle term has a negative sign, that tells us that both factors of 4 will be negative. Now the number 4 has 2 factor pairs, 1 and 4, in addition to 2 and 2. So again, we have to start somewhere. So let's begin with 1 and 4. Both numbers will have the same sign, both negative. So let's go ahead and put minus 1 in the first binomial and minus 4 in the second. Now before we go any farther, notice that based on this placement, the second binomial has a common factor of 2. which cannot be possible since our original trinomial had no common factors. This tells us that we've placed 4 and 1 in inappropriate places. So let's switch them around and place the 4 in the first binomial and 1 in the second. We are confident that 5x times 6x gives us our 30x squared, and we're confident that negative 4 times negative 1 gives us our positive 4. We now check the sum of our inner product and our outer product. Our inner product gives us negative 24x. Our outer product gives us minus 5x. If we add those two terms together, notice we get negative 29x. And negative 29x is exactly what we wanted to get. So the factored form of 30x squared minus 29x plus 4 is equal to 5x minus 4 times 6x minus 1. The difference of two squares. We begin our discussion of the difference of two squares by multiplying a pair of special binomials. These two binomials in example 1 are special because their terms are the same, but the operations connecting those terms are opposites. That is, in example 1, we have x plus 9 times x minus 9. So let's multiply. Applying the distributive property, we multiply our first terms together to get x squared. We multiply our outer terms together to get negative 9x. Our inner terms give us plus 9x, and our last terms give us negative 81. Notice that the two middle terms, the ones obtained by our inner product and our outer product, cancel out. And we end up getting a final answer of x squared minus 81. Unlike our previous examples, when we multiply these two special binomials, we get a binomial as a result, not a trinomial. This binomial is called a difference of two squares, because if you notice, x is being squared in the first term, and 9 is being squared in the second term, and the operation of subtraction is occurring between them. Hence why we call this the difference of two squares. In example 2, we're asked to factor a difference of two squares. We know that this binomial is a difference of two squares because the first term is x squared. The second term can be written as 6 squared, and we are finding the difference between the two. Based on our observations in example 1, we know that a difference of two squares can be expressed as a product of two special binomials. These binomials have the same terms, but their operations are opposites. Notice that if we multiply these two binomials together to check our answer, we get first, outer, inner, last, and the fact that the operations are opposite cause our middle terms to cancel off. resulting in the same binomial that we started with. So the factored form of the difference of two squares, x squared minus 36, is equal to x plus 6 times x minus 6. In example 3, we're asked to factor the binomial 9x squared minus 1. Notice that the 9x squared can be written as the quantity 3x squared. Furthermore, 1 can be written as 1 squared. So what we have is a difference of two squares. And we know that to factor a difference of two squares, we take the two terms that are being squared, connect them with an addition sign, connect them with a subtraction sign, and multiply those two binomials together. So the factored form of 9x squared minus 1 equals 3x plus 1 times 3x minus 1. The binomial in example 4 is 25 minus x squared, and we're asked to factor. Again, notice that the first term can be written as 5 squared, and the second term is x squared. So we have a difference of two squares that can be factored as 5 plus x times 5 minus x. Factoring completely. When we are told to factor completely, we always begin by factoring out the greatest common factor. So consider example 1, in which we're given the trinomial 20x squared minus 14x plus 2. Looking at each of the terms in that trinomial, we notice that each term is divisible by 2. Therefore, we can factor out a common factor of 2, leaving behind 10x squared minus 7x plus 1. Now we notice that we have a trinomial written in descending order. If this trinomial factors further, it can be written as a product of two binomials. Recall that to factor a trinomial, we look at the first term to determine the factors that appear as the first terms in our binomials. So the factors of 10x squared depend upon the factor pairs of 10, which include 1 times 10 and 2 times 5. Furthermore, the factors of the positive 1, the third term in our trinomial, will go in the back of the binomial. Since this term is positive, that tells us that the factors of 1 that are to go in the back of our binomials will have the same sign. Furthermore, since our middle term is negative, that sign will be a negative sign. 1 has only one factor pair, and that's 1 times 1. So that means we can place minus 1 in the back of our binomials. That helps us to determine which values of the factors of 10 to place in the front with our x. So choosing the factor pair for 10 that involves 2 and 5, let's place 2x and 5x in the front of each of our binomials. Checking to make sure that we have properly factored our trinomial, we multiply our inner product, getting negative 5x, our outer product, getting negative 2x. Adding those two terms together, we get negative 7x, which is what we needed to have. So, the factored form for 20x squared minus 14x plus 2 is equal to 2 times 2x minus 1 times 5x minus 1. In example 2, we're given a binomial. As before, since we're being told to factor completely, we must be sure to factor out the greatest common factor first. Looking at the two terms in our binomial, we notice that each term is divisible by 10. So we can divide out a 10, leaving behind x squared minus 4y squared. Considering what's left in parentheses, we notice that we have a difference of two squares. The first term is x squared. The second term can be written as the quantity 2y squared. Once we've identified the two terms being squared in our difference of two squares, we can continue factoring, writing our final factorization as 10 times x plus 2y times x minus 2y. And now our expression is factored completely.